Hello everybody, welcome to another tutorial for VAST Lite. In this tutorial I want to show you how you can use vasttools, a Matlab script, to export 3D models from your traced objects. The exported models can then be loaded into 3D rendering programs like Blender or 3D Studio Max. So to start up, I have loaded VAST Lite and I opened the Kasturi dataset, high resolution, which is available on the web page, and the segmentation that is also available on the web page. So we can, if you look here, we can select some object and then go to its anchor point just by clicking home. And if you zoom in, you can see this object is a spiny dendrite which has lots of spines on it. And there are tons of objects labeled here. So this is, however, a voxel representation at the moment. So I just paint over the images and I get regions which are just groups of pixels that belong to one object. So now if I want to render this in a three-dimensional way using a render engine or professional rendering tool, what they want to have is a surface representation which consists of triangles with corner points and definition of what corner points belong to a single triangle, which describe the surface of the object. So we have to somehow translate that into this other format. So in VAST there is a API which you can use to link to a script in Matlab that is also provided with VAST. And you can find that in the supplementary tools. So if you look here, so VAST tools is included in the VAST package that also contains the manual. You'll see a link below which shows you another tutorial that explains how you can download and open this or save it out from VAST. So VAST tools is in this folder and it has another subfolder that contains scripts that are called. So it's important that you unpack this from the zip that is provided into an actual directory so that VAST tools, when it's run by Matlab, can actually find these scripts in a subfolder. So .m means it's a Matlab script. So if you have Matlab installed, you can just double click this and then Matlab should start up, which can take a few seconds. And then you get a screen that looks something like this, and then it will also open a window that looks something like this. So this is the whole script that is provided with VAST, and you don't have to worry about this, you just run it. So you click this run button here. And what will happen is you get another window pop up that looks like this. And this contains all the functions that you need, and it has a user interface, so you don't have to worry about the scripts. So we can maybe just hide these. And this one too. So now, since this is running in Matlab and not is a different program than VAST, so we have to make a connection between these two. And the way the API works in VAST is that you enable a connection within VAST that allows remote programs like this Matlab script to connect to VAST through TCP/IP. And you can open this under Window Remote Control API Server, this sub window, in which you can enable the TCP/IP functionality. So there are some ways to just click enable here and it will be enabled. There are some ways to restrict that to particular IPs or use a particular port. And then also everything that's being sent between the client and VAST, which is the server, will be documented here so you can check what's going on. So once this is enabled, you can connect to this from VAST tools. And the way this works is you just go to this window, you go under connect, you say connect to VAST. So now you can see that this changed to disconnect. You can disconnect here or reconnect. And then also you can see that VAST notices that the client is connected. So once you have established this connection, the client, which is running in Matlab, can request data from VAST and can also remote control some functions in VAST. So the function we want to use here is the export function to make three-dimensional models. And if you go under export here, you can see there are a number of options of different things you can export, but right now we're going to concentrate on this function here, export 3D objects as OBJ files. So OBJ is a format that is very common, and I think you can probably load these files, these OBJ files that are made in any three-dimensional editing or rendering software. So if you click this, there will be a dialog opening. So this is also from MATLAB. So essentially this script opens that window, and you have a ton of options here, what you want to export, at what resolution you want to export it, where you want to save it, how you want to name it, and so on. So let's go through this from top to bottom. So in the top here you can choose at what resolution you want to export. And the resolutions you can choose from are the MIP levels, which are like powers of 2 reduced resolutions of the voxel data or the pixel data that you have in VAST. So the lower you go here, the less triangles will be produced, but also the less detailed your model will be in the end. So what I normally do is I go to a resolution that is in X and Y approximately equal to the Z resolution, which makes triangles that are approximately isotropic in space, or the corner points of the triangles will be more or less isotropic in space, which leads to more smoothly looking objects in 3D. So let's choose this MIP level 3 here, so it's slightly lower in X and Y than it is in Z. Also, the higher MIP level you use here, not only the less triangles will be produced, but the consequence is also that it will be much faster, and also the file sizes will be lower. So if we want to demonstrate this quickly, I think I'll just use a lower resolution here. The next, you can choose a sub-region from the whole VAST dataset from where you want to export, or you can set it to full. So each object has a bounding box internally that kind of represents where it is in space, and you can use this bounding box to restrict from which region you want to export. So you can set it to selected bounding box. So for example, if I choose one object, so to make this clear, let's choose a spine here. So this, and also to make this clear, let's change this so you can only see the spine. Do you see that in green here? So let's say we just want to export the spine here. So you select it, and this spine has a bounding box which you can see under segment information. So you see the bounding box of this spine is from these coordinates in XYZ to these coordinates in XYZ, so it's not that large. So if you export this object, and VAST has to load the whole data set from 0 to the maximal extent and then extract this little part of it, that can take a very long time. But if you restrict it to just the region where this object is, the export will be a lot faster. So right now it's set to full, and you can also click this to set the coordinates to full for the area that's to be exported, but you can also just set it to the selected bounding box. And what will happen then is that it just requests the information from VAST where the selected object is located, and it fills in these fields here. So you don't have to find that manually, you can just use the bounding box of the object. Another way to specify a region is by setting it to a current voxel that you set by moving VAST to that location. So there's this center cross, which you can barely see. Let me make this a little bit more obvious. So you can adjust the brightness of this in here. So let's go to 128. Okay. And you'll see now the center cross here. So that defines the coordinates that are being shown in the coordinates window. And it also can be read by VAST tools and be used to define a corner of a region to be exported. So keep in mind that this is actually three-dimensional, and if you want to set the minimal and maximal slice, you have to also place corners in the minimal and maximal extent in Z. So let's place the corner over here, because I know the spine will be somewhere here, so that should be outside. And then we just go to VAST Tools and we say set to current voxel. So now it just sets it to one single coordinate, which is this. Now I go to the other end of the spine. So here's the spine. I go to the opposite direction with respect to the center cross. So the center cross is now here, and the object is left and above from it. And also we are at the, well, somewhat below the end of where the spine is located in the volume. Now if I say extend to current voxel, now it will actually keep the minimal and maximal extents of the voxel that was set previously and the current voxel. So you can do this several times with different points, and kind of use that information to span up a region from which you want to export. So that's what these functions are doing, or you can set it back to full if you want to make sure that everything is exported. Because the bounding boxes can sometimes be a little bit off, especially if you paint and then you erase. VAST doesn't really know where the voxels are. It just knows that you did use a certain region for painting, and then it only extends the bounding box but never shrinks it, so that bounding box region can be much larger in some cases. Anyway, so let's set this back to bounding box. It seems to be correct in this case. Now to export it, vasttools needs to know what the voxel size is to scale your object correctly. So it can request that information from VAST if the voxel size is set correctly. So if you go under Info Volume Properties here, you can see what voxel size is stored with the electron microscopic file, and this is correct in this case. So typically, when you import an electron microscopic dataset or light microscopic, you will be asked by VAST to provide these numbers, and that will be used later to scale the three-dimensional object in the export. So this has been read from VAST and it's correctly set, so we don't have to worry about this. This scale here is used to reduce the general numbers that are put in the object file. So I'm setting this standard-wise to 1,000th, which means that if the unit that is used in VAST is nanometers, then we will have micrometers here, which is a much more appropriate number, region, or scale for three-dimensional render programs. So typically I just leave this as is. Then I don't want to introduce any offset, which means if you export several objects from the same volume, they should all be in the same coordinate system. So if you load them together in the three-dimensional render engine, they all appear in the right place. But you can change that if you add an offset here, but I don't need that at the moment. Then this processing block size is an internal amount of data that's being processed at a time. So what happens is that image data will be loaded from VAST block by block into MATLAB, and then the surface will be extracted just on each block. Then afterwards I have to put together the surfaces of a single object from all these cut up blocks, and this specifies the size of each block. So typically you can just leave that as is. More important is the setting here, which defines what you want to export. So right now, just to make this fast, I'm going to export only the spine, so I don't have to select all segments. I will just choose selected segment and children uncollapsed. So this doesn't have any children. See, this apical spines folder has a lot of children, which are these spines, but this object doesn't have one. So that would give me the same result if I say selected segment uncollapsed or collapsed. But in a case, let's say I would want to export this. So now if I close this folder, this will be treated as a single object if you select in the export selected segment and children collapsed as in VAST. So in this option and with the closed folder, you will get just one object that contains all the spines. If you want to have each spine as a single object, you can just open this, and then each spine will be treated as a single object in this mode, because it's not a collapsed folder. So what will be exported is this folder segment, if it has anything labeled, and then all the children of it, and it will be all treated as individual objects, except, for example, here, this double spine, which has a closed folder, will now become one object if you do it like this. But you can also choose selected segment and children uncollapsed, and in that case it will completely ignore what the children's folder state is, whether it's collapsed or not, and it will just treat every single object as a separate object to export. Okay, so I think we were using this. Which one were we using? The first one? Well, whatever, let's just use spine number 4. I think that was the one. And where's my window? Okay, just to make sure, set to selected bounding box, so that was the same apparently. So for the exported meshes, of course, you need to write them to files. So the file can have a file name prefix, which you can set here. Let's just set this to spine, for example. And then this option here, object colors, you can set this to object volumes as jet color map, but only if you previously computed volumes. So I'm just going to ignore that for now. You can compute volumes in a different function in VAST tools, and then you can set that so that the objects will all get an object color that depends on their volume. So like this you could visualize which spines, for example, are larger or smaller. But right now I'm just going to use the colors that are assigned to the different objects in VAST. Then you have to choose a target folder. I'm just going to leave this as is for now. And then here's several options that you can set if you want to have the folder names in the file names. So that will allow you later, if you load these objects into a 3D render engine or analyze them in another way, that you can identify where the object was in the folder tree, because all the names of the different folders will be included in the file name. This can, however, generate pretty long file names if you have a deep folder structure like here. So this file name will now be objects neurons objects.neurons.dendrites.spiny dendrites.bobby's dendrite red and so on. So this may generate a file name that is way too long. But in many cases this is very helpful. So for example, if you load all spiny dendrites and other dendrites into a 3D render engine, and now you want to make all dendrites red. So if you can use a search function for the object names and just say, I want to have only objects that have spiny dendrites as part of their name, you will only select objects that are within that folder. And then you can just assign a color to those objects only in your 3D render engine. So that can be very useful. The next, write 3ds Max bulk loader script folder. This is specific for people who use 3D Studio Max as a render tool. There is a scripting system, and I wrote a little script that you can have written to that folder, in which the object files are stored. And if you just run that script, it will load all the objects in that folder at once into your scene in 3D Studio Max. So otherwise you would have to import each single one, which if you have thousands of objects is not really what you want to do. So that is very useful in that case. Invert z-axis. So in VAST, typically I interpret the slice numbers as going down. So you start at 0 and you go down, just because that's the order in which the sections are being cut from a block or collected on a tape. So you start from the top and then you go down. So to reconstruct the objects correctly in 3D and not to flip them in Z, you have to invert the Z-axis. So as this number goes up, the Z should go down. So this is what that function does. You can uncheck that if you want to. Closed surface sides will make solid objects. So even if the object leaves your three-dimensional cube of data, at the side it will have a closed surface, so you cannot look inside the object, but it looks like a solid object. You can actually also, as you export objects, compute the size of their surfaces if you enable this. And if you really only want to compute the surface sizes, you can check this to skip the model file generation, which will speed things up. The surface statistics is computed just by summing the areas of the triangles, which are computed from during the mesh computation, and then this will be stored to this text file, which you can interpret and then, for example, use to estimate the surface of a certain object. That is a little bit limited in accuracy, just because the objects can be rather rough because they are generated from voxels. So the surface that you may get out of this can be overestimated compared to the actual biological object. So just keep that in mind if you want to use this function. Anyway, so now if I just click OK here, what will happen is that very quickly you can see here the segmentation of that region, of that spine, was requested from VAST and then transferred from VAST to Matlab, and then Matlab analyzed it and saved the object. So that went so quickly that we didn't actually see it because this window wasn't activated. So now we have a file on disk that contains the object as a mesh. So you can see I just wrote this here to the same folder. So and it's a rather long name, as you can see, as I explained earlier. There are two files that were written. One is the OBJ file and the other one is the MTL file, which is the specification of the material for the OBJ file. If I just open this and show you what that looks like, it's really just coordinate triplets for vertices. So each V here means it's a vertex in X, Y, Z coordinates. And then later there's a list of faces, F, which just index the corner points of each triangle. So like this, you can specify a whole set of corner points and triangles which constitute a mesh. And then also this is linked to a particular material which is stored in the MTL file, which has the same name. So the loader will know which material belongs to which object. And that just specifies its color and other surface properties, which are exported. So now you can take this OBJ file and just load it up in a render engine. Maybe I can show you this with my version of 3D Studio Max. I'm just going to open that. Oh yeah, also while this is opening, this is the script which I write that you can run, and we can maybe just try that in 3D Studio Max. 1 second. Yeah, this may take a few seconds to open. Elevator music. Ah, here we go. 1 second. Okay, maybe I should show this. So, how could I do that? So, this is the I cannot actually. Anyway, so 3D Studio Max opened, and I can choose, if I run a script, I can choose the script here. I load that, and then it will load these objects in the same folder. Here's the 3D Studio Max window, and what it just loaded is really just a single spine, which is located in the correct place with respect to the global placement in the three-dimensional cube. So if you load lots of objects here, you would be able to see them all in the same place. So this was the object we just exported. So now you can set up a camera and lights and an animation, and then render a three-dimensional animation through your scene, including all the objects that you traced in VAST if you want to. Okay, so I think that concludes this quick introduction into using VAST tools to export objects, and I hope that it is helpful. Thank you.